Thank you, Eric. Thank you for giving me a chance to present my research to this elite audience. Martin and others have already presented a lot of details and a lot of things about the static model and twilight phenomena and all that. Here, I'm going to talk slightly in a different format where I would be talking in terms of seeing if we can resolve some of the problems which were related to so-called impossible early galaxies problem, if it can be resolved by a combination of the twilight in the expanding universe model. So this is, let me see, I'm not able to, okay, I have to use this mouse to change. All right, so here is, I still have my thing covered. Somehow I have to remove this thing here. Yeah. So the, how come it is showing? All right, it is still covering some of my presentation with something else. I'm not sure. Participant alien closed captioning. Okay, let me see. Oh, let it be. All right, the outline is actually, I would talk about James Webb Space Telescope Cosmic Dawn Observation, which is impossible early galaxy problem, what it is, and resolving it with lambda CDM requires unrealistic galaxy formation models. So, and resolving with the twilight, it has some other problems which were already discussed with earlier presenters. Resolving with covariant coupling constant model, which is a new model which I will briefly talk about. And that is also unsatisfactory. But the hybrid model I consider are the lambda CDM plus the twilight model and the covariant coupling constant model plus the twilight. And we find that only the covariant coupling constant and the twilight combination is satisfactory. And not only that, it fits the supernova 1A data as well as the standard lambda CDM model. And then how about, does it fit really the CMB, BAO, BBN, globular cluster data and all that? Actually, that has to be done. I have done some work on BAO at this point, which I will present, but other things are yet to be done. James Webb Space Telescope observations are essentially, they are early. Okay. The excessive large number of galaxies at very high redshift, which around Z equal to 15, 10 to 15, or so, even higher. The universe age at that time was only about 0.3 gigayears. This is not foreseen by the standard cosmological model. Galaxies at these redshifts have disks and bulges, which indicate that they have passed through a long period of evolution. And spectroscopically, these galaxies resemble their counterpart in the local universe. Smaller galaxies are more massive than larger ones, which is quite the opposite of what one expects. Now, some of the problems we can see are in these. In this slide, which is essentially the image which NASA and the European Space Agency has produced and showing the images of 6 candidates of massive galaxies, which are in existence only about 500 million years after the Big Bang. And this one at the bottom, really left, it could contain as many stars as our present-day Milky Way galaxy, and it's 30 times more compact. How can it be? I think this was also considered by some other presenter, and this is one of the galaxy which is it's called the Mazy galaxy, and it was detected essentially considered to be only 390 million years after the Big Bang. It makes it one of the earliest confirmed galaxies ever observed. And this is another one at glass Z12. And this particular galaxy makes perhaps the oldest one spectroscopically confirmed galaxy, and with a mass of 10 to the power 9 solar masses. But size, according to lambda CDM model, is only 1 kiloparsec. Whereas with the new model, which I have proposed, it's about 10 kiloparsec, which is more in line what one would expect from such galaxy. Now, this kind of graph has already been presented earlier, and that I don't think I need to discuss that in detail, except that to say that the twilight model definitely appears to be fitting the James Webb observations better than any other model, whether it is the linear using the Hubble's law or the lambda CDM model. And this produced by Rajendra et al. Is definitely was instrumental in my considering the hybrid model, because I knew that this fits the data very well, but then the twilight model doesn't fit the supernovae data as well. In fact, not at all well, without, of course, adding some additional correction or something. Even then, it doesn't fit entirely well. So that is the instrumental in my considering this hybrid model. And this lower graph really presents the same thing in a different form in terms of the size of the galaxy instead of angular size. Here is physical size galaxies. Now, we have already talked about the twilight, why twilight observations are in conflict with why they are in conflict with the observation, like CMB observation. And I think Eric has explanations about it quite a bit, that how it can explain CMB observation or anisotropies and everything. But most people don't believe those kind of things. But twilight can't fit the supernova data as it fails the Tolman surface brightness test. And then there is a question in the last lecture or talk we discussed about the twilight effect. What causes the twilight effect? And that is still very uncertain. It's not really completely clear what causes that effect, because many of these Compton effect and all those could be causing blurring of the images, which is not seen. Now, the hybrid model is, what is a hybrid model? Now, if we consider a twilight model and expansion model together, then proper distance covered is the same. So this is very important thing. It can constrain the parameters which we can use. So we don't need additional parameter for the twilight components. And then lambda CDM plus twilight, this is the first one I tried, because naturally when I wanted to try something let me try the lambda CDM plus starlight, but it doesn't fit the James Webb data. Then the CCC covariant coupling constant plus starlight model, that gives an excellent supernovae data fit as well as a great James Webb data fit. But it increases the age of the universe. That was my major concern. It increases almost doubles the age of the universe. But they fit the galactic angular size data very well. Now, supernova data, if we see, this one, supernova data, it is a very critical thing for any model, cosmological model, to fit before it can be taken very seriously. That is what I have learned. But that means all the data, lambda CDM, the covariant coupling constant model, I will just describe this covariant a little bit later, plus starlight model in lambda CM plus starlight, they all fit these data very, very well. So they all qualify for further testing. Now, let's try to see the parameters. The parameters here are the first is the H0, the Hubble parameter. Hubble constant is for all these models which I am discussing are the same, almost the same. And there's one I have added in the Starlight Plus model, in which I have put additional Starlight only need H0 otherwise, but I have put additional parameter to account for anything missing in the Starlight. And that could be the expansion of the universe or something else, but that is a missing factor, which when I put that missing factor, then I get these things, and they are almost the same within the uncertainty, except the pure Starlight model, which is low, quite low. Then we consider what is the fraction of this, which is in case of the in case of the when you are talking about the combined models, then we have to see what fraction of the Hubble constant is due to the expansion of the universe and what is due to the Starlight. And you see they are, for these two models I have considered, they are not very different. And the fit parameter, which is the chi-square fit, which is almost about the same, not very, very different, except for just pure Starlight is so off, and definitely it doesn't fit the data well. Number of free parameters, the same for these ones, which are giving almost the same results here. And of course, in Starlight, only H0. Now, but age of the universe, for lambda CDM and covariant coupling constant model, they are the same, almost the same. But these parameters, the age, when you add the Starlight, then they both increase. The lambda CDM plus TL goes to 19 billion, and this goes to the other one, 27 billion. So these are the significant changes is really in the age of the universe. Now, angular diameter distance, if we see in here, angular diameter distance changes quite significantly when in comparison to the, see, this is the lambda CDM model, which is, and this is the CCC, that is covariant coupling constant model. Then lambda CDM plus TL model doesn't change as much. This one is the CCC plus TL model, and that one is just the TL plus, not TL, but TL plus model. I just wanted to make sure they are comparable in terms of the free parameters. see where it is peaking. This is peaking in a very low value, about 1.6 or something in case of lambda CDM. Here the peaking is happening at very much higher Z, about 12 or 13. Now, if we see the universe age as a function of Z, then we find at Z equal to 10, which is of great interest at the for the early galaxy, impossible early galaxy problem. It is about 10 times the age of the universe at that Z10 is almost 10 times the lambda CDM model. So that provides a lot more time for galaxies to develop. Instead of few 100,000, you are talking a few billion years for the creation of these galaxies. Age ratio, the same thing presenting in a different format. The ratio CC plus TL divided by lambda CDM is here, and this one lambda CDM plus TL divided by lambda CDM is here. It also increases the lambda CDM plus TL also increases the age of the universe at Z equal to 10, but not so much as the CC plus TL. Now, twilight as a fraction of expanding universe redshift. This one, again, you see is shown in this, that how much is contribution coming from twilight and how much coming from X. It remains almost constant for significant time here in case of CCC plus TL compared to lambda CDM, but both have a contribution, significant contribution coming from the twilight. But at higher value, it increases. The twilight contribution becomes much smaller, much smaller than the expanding universe model. This is the actual size of an object as compared to the observed size. So if in the case of lambda CDM, this is as it's shown as what you might see times the lambda CDM size. So if lambda CDM size is 1, then what is the size you will expect to see the physical size of the object? You can see it is showing to be 10 times more around this, Now this is a graph which is showing the angular size. It is the same kind of graph which Levigen has produced, except that here we have put various other lines, theoretical lines as well. And you see, here is this thing, the twilight model only, and this one is a CCC plus TL model. And they are not very different. Within the error, they appears to be showing a similar kind of fit. And this is perhaps the most important graph on this paper. The angular size is here 10 times smaller in the case of lambda CCC plus TL model compared to some other model except the twilight model. Now, if we go into the BAO, then BAO acoustic scale, it has a correlation function for the galaxy separation, which comes out to be about 150 megaparsec. And when we try to fit this BAO data using lambda CDM model and the CCC plus TL model, they are about at the same place, as I will show here in this one. The BAO acoustic scale, what we did, we calculated this angular size of the sound horizon. It is the angular size we measure. We don't measure the physical size. So when we calculate the angular size of the sound horizon, which is using the Planck observation at the surface of the last scattering, that is reported about 0.60 degrees by the Planck, and the baryon density, if we set the baryon density in our model to be 17% of the matter density, then we get the same value as the Planck. Now, another thing is to see BAO at a lower Z values. That is the absolute scale of BAO estimated at low redshift from measured angular galaxy distribution power spectrum. And using the two models, what we get these kind of fit to the data. And this line has no real meaning because of large scattering, so we should only consider weighted average. This comes out to be 151 plus minus 5 megaparsec for CCC plus TL model, and for the lambda CDM model, it comes out to be 145 plus minus 5 megaparsec. So this is about the same, because within the uncertainty of these numbers, it is about the same. Now, the global cluster thing is one thing which is used for determining the age of the universe. A globular cluster age cannot be more than that of the universe. But many of the globular cluster stars have shown, or cluster has shown, that the age is higher than that of. And every time it happens, then people try to adjust the model, because cosmological model used for determining the age of the universe has nothing related directly to the models used for stellar evolution models, which are used for determining the age of the stars or clusters. But this is where I'm trying to show one of the author, after he heard about my paper, they were able to submit this paper in the archive and send it for publication. Before that, they were very hesitant. There must be something wrong. So I think it does provide people the increased age of the universe, provide people freedom to have a different stellar models, or maybe flexibility in having stellar evolutionary models. What is covariant coupling constant? Covariant coupling constant is based on the energy conservation, essentially. Energy conservation is, this is gravitational energy, mass energy here, thermal energy, photon energy, electrostatic energy. They have to have local conservation laws. They must be related in this way. Otherwise, there will be a breakdown in the energy conservation. This leads to essentially this relation. And if we assume mass and electron charge and this fine structure constant to be not changing, invariant, as people have observed, and distance measured with the speed of light, then essentially we get this kind of relationship. A scale G has to scale as C cubed, KBCHC, and that leads to this relation. I'll try to hurry up because I seems to be running out of time. So the variation of all of these can then be represented in this kind of format. That means if we constrain one, we have to constrain all, because their variation represented by one simple function. I don't say they vary, but if they vary, they have to be allowed to vary together, not choosing one to vary and keeping all the other fixed. You automatically fix. If you fix one, you automatically fix others. This is also can be seen by the relationship of the dimensional ground, how they should vary. And this is I'm plotting the chart of the variation. It is increasing in the past and compared to the current value. Current value is given here, and G increasing, KB and Planck constant, and here is speed of light. And we find the lot of variation of G which we have seen, and constraining the variation G is dependent on the Kepler's law. And Kepler's law, this one, is period square is 4 pi r cube over Gm. Now, R is varying as C, G is varying as C cubed. So essentially their variations would cancel. So you will never see any variation in this. You cannot constrain the variation of G by observing this. This is what I'm trying to show here. Same gravitational lensing. Gravitational lensing has a ratio. It involves path lengths, changes, quasars detected with different path lengths. I'm not going to go into detail again because of limited time. But here you see Gm over C cube. G in varying as C cube, so their variation will cancel. You will never be able to detect the variation of C or G using this method. Same is gravitational waves constraint. Again, it depends on G or C cube. So we have to design some experiments which can unequivocally confirm or falsify the predicted variation of the coupling constant. What is that experiment? Coupling constant variation do not cancel. That's the, we have to find that thing, experiment. And measurement accuracy has to be 1 times 10 to the power minus 10 or better. Now, in the CCC model, this is essentially what we have done. We have just changed this FLRW matrix. Metric is changed because we have to allow the variation of the speed of light and also the variation of distance as the speed of light. When we put that together, we solve the Einstein equation and find Friedman equation. We find that H is reduced by is replaced by H plus alpha, where alpha is the ratio of the variation F dot by F, where F is what gives you the variation of the constants. And here again, because distance traveled is the same in both the cases, in the case of tired light, as well as in the case of co-varying coupling constant, that can constrain how the Hx and Ht, expanding universe component of Hubble's constant, and this. So major concern in the media for this has been no 2 parameters for both, but they say, oh, you have more than 1 parameter, too many parameters. Not too many parameters, it's just wrong. Time dilation observed is not included in this. Yes, it is included because this CC plus TL covers the same distance. There's no separate time dilation. Twilight adds blurring effect. We talked about that before. Is definitely that is a concern when we have any competent scattering, but alternate methods could be used. We don't suggest what is the method of twilight. It does not preserve the CMB black body spectrum, but we have shown in the recent paper that it does preserve the black body spectrum. Constant variations are not detected. As I said, it will not be detected unless we have a special equations or a special experiment which can detect it. And that's about it. In summary, I can just say we resolve the impossible early galaxy problem consistent with CMB first peak and BAO data. It yields baryon density the same as lambda CDM model. That is about 5% of the critical density, not in conflict with globular cluster ages, 13.8 gigayears, which is sometime in conflict with constant variation prediction, not in conflict with observation. So immediate future work we are planning is CMB spectrum fit, BBN abundance, and globular cluster age. That's the end. Thank you very much for your time. I appreciate it very much.
Okay, thank you, Rajendra. Although you did run a little late. So we're just going to take two quick questions. The two Alessandros, I guess Trinchera goes first.
Yeah.
Oh,
Professor.
I'm sorry. Martin has not asked a question. Well, no, you haven't asked a question either. Alessandro go first, and then Martin, then Alessandro.
Thank you so much for your presentation. Very interesting.
Thank you.
You clearly plot the angular diameter distance, which is different between the cosmologies. So clearly between tidelight and the lambda coordinate meter. But before you stated that the proper distance is the same between tidelight and the lambda coordinate meter. Can you please explain this part?
Yes, this is a good question. The thing is this, that the tired light, after all, the source which is emitting the light is at a particular distance. So whether now tired light is happening in parallel with the expanding universe. So distance does not increase or change. So when we calculate the tired light, we say this is the distance d. When we calculate the expanding universe component or redshift, that distance is still the same. And that is very important because that distance cannot change. The distance of the emitting source is the same, whether you use starlight concept or you use the expanding. And we are using both of them. And here, let me show you in the equation here. What we have here, dpx, this is for expanding universe part. I write in the CC case, this comes out to be the number, and the proper distance of light this. Then we have to take in the low distance, low dp limit, very short limit, and we compare this, and this dp and dpx are equal. Or we set dpx minus dp t equal to 0. And then that will constrain my parameters in there, and also how z is related to zt and zx. This is zx here, you know.
Okay, thank you. I will check later the equations when
Okay. Yeah, you can check in my paper. That will be the best.
Yeah.
Okay, Martin.
Hello, just a quick question. In
Yes,
a
Martin.
universe with 25 or 26 gigayears, one would expect many objects in the local universe to have this age of larger than 20 gigayears, many galaxies with more than 20 gigayears, and we don't see galaxies of this age. What do you think?
See, this is a very interesting question, because if all the galaxies are produced at the same time, then you might say, yes, we should have that. But then one of the things we have to see, what models are used for the creation of galaxies. You have to, they are all developed based on the constraint on the age of the universe. So we have to, once we relax that constraint, that this is not a constraint we have to apply, then your models will be perhaps different. Just the case in case of this one I cited to you, the one I showed here. No, not that one. This one. It came out just very recently. It hasn't. I don't think it has been published yet, but it was submitted to archive. And this one is giving the age of the globular cluster through straggler stars modeling to be 19 to 20 gigayears. So I think one has to see what comes out once this constraint on the age of the universe is relaxed.
Okay, last question, Alessandro.
Yeah. Yes, it seems to me, thanks for the talk, it seems to me, nevertheless, that the Z measured as static or Z as measured as the redshift quite differ and quite depend from the distance, in the sense that the usual redshift is integration of a Doppler. On your main hypothesis, you're saying, well, we combine the expansion shift with the static shift. Now we use this hypothesis since few years, but we have used both a shift towards the red or towards the blue. The problem is that, to my knowledge, there is no published or a serious journal theory that says that there is a tired light effect only towards the red. So I think that the main message from this conference is that cosmologists, astrophysicists should concentrate on the mechanisms producing shifts different from the expansion. Okay.
Yeah, yeah. I think your concern is right, whether it is red shift or blue shift. But here you might say that we are considering it is a red shift. We are saying, for example, if a vehicle is moving on the road, there is a resistance due to drag and resistance due to the road. And there are two things which are really burning the fuel in the car. So
Yes,
this thing, what we believe is happening in this case, is still covering the same distance. Car is covering the same distance. So that's what constrains the parameters of the two phenomena happening together.